Welcome to our iRay seminar series. I have the distinct pleasure of introducing our distinguished speaker today, Professor Richard Zemel. He's a co-founder and research director of the Vector Institute, professor in computer science at the University of Toronto, soon moving to Columbia University, a senior fellow of the Canadian Research and a Google NSERC Industrial Research Chair in Machine Learning. Supplementing his outstanding academic record, Richard is also actively promoting the spread of machine learning techniques to tackle real-world problems, having co-founded Smart Finance, a fintech startup, and being the chief scientist for machine learning in the Creative Destruction Lab at the Rodman School of Business. Richard's work has been honored by many prizes, amongst them the NVIDIA Pioneers of AI Award, a young Investigator Award from the Office of Naval Research, a Presidential Scholar Award, and he has been the recipient of 2 NSERC Discovery Accelerator grants. He sits on the executive board of NeurIPS, which is also using his Toronto paper matching system, a popular way these days of matching reviewers to paper submissions. Before I hand over to Richard, let me mention that you can ask questions also during the talk in the chat facility of the platform from which you join, so Zoom or YouTube, and I will communicate them to Richard. Moreover, it would be great if you could fill out a short survey we will send out by email afterwards for us to improve our format. The questions Richard proposes to address in his talk today are close to my heart and are fundamental to scaling and building effective ML systems. I, for one, cannot wait. So Richard, without further ado, I yield the floor to you.
Excellent. Thank you very much. Let me share my screen and I'll get started here. Okay, so today, yes, I'd like to speak about building agile machine learning models. And to start, so deep learning has driven all kinds of progress in areas that have, made it through the media a lot these days, starting with, some of the original work in image classification and speech recognition, and, very actively pursuing things these days in things like autonomous driving and machine translation, and the well-known successes in games. And the way that it typically works is that you train a very large neural network on a lot of data for a particular problem. And today, what I want to focus on are more challenging scenarios with the aim of moving towards agile machine learning models. So what do I mean by agile models? One is that we'd like models that can learn from only a handful of examples. So I'm going to tell you a lot about few-shot classification, which is towards that aim. The second question is, how do our models learn when the test distribution has been shifted relative to the training set? So how can we generalize to new domains that are different than what we train on? And the last one is a bit surprising. I want to show some synergies between domain generalization, like the second point there, and a different field known as algorithmic fairness. Okay, so that's the outline of the talk. To begin with, the standard machine learning setup is that we learn and evaluate in the same environment. So here we have, each example is a little circle. We have 2 classes, the blues and the reds. That's our training set. Our system builds a classification boundary like this. And then we get test examples. We do very well when they're drawn from the same distribution. But what happens when we want to, have a new task at test time, right? So let's say our examples were pedestrians and cars, and a self-driving example. We do very well at classifying those. Now we have to adapt to a moose that we've never seen during training time. Okay. So towards that aim, we look at few-shot classification. So here the input, we have a large labeled data set for a set of training classes. So what's illustrated below is we're going to have lots of examples of dogs and mushrooms and fences, right? So that's our typical kind of offline training set. But now what we want to do is have that be able to generalize and have a model that can learn new classes from few examples. Right? So it's not that we want to test it on dogs and fences and mushrooms, but on wholly new classes and see how well it can generalize to that. So we call that few-shot learning. It's going to learn with just a few examples of these new classes. So it's important in the real world for this because lots of real-world problems have insufficient training data. And we may have offline lots of training data, but we don't know what that model should be used for at test time. And so really what we want to do is have a model that can adapt and leverage the previous knowledge, not to do well on new examples from the same classes, but to learn new classes quicker. All right, so that's what few-shot learning is all about. So here's an example showing the top row. We might have, a case where we have 3 so-called support examples. That these are new classes, right? So we have a vase, dogs, and a spider, or a crab. I'm not sure what that is. We have one example of each of those. So that's called one shot, one labeled example of each of the classes. And then at query time, we're given new examples. We have to classify amongst those 3 classes. And then down below in the second row, we have 3 new classes, buses. I'm not sure what those things are, mugs, and also dogs, different kinds of dogs, okay? There's been a number of paradigms, in this paradigm, a number of benchmarks that have been developed. One famous one is mini-ImageNet. So that's taken the original ImageNet, image classification benchmark and built a smaller one in this few-shot setup. So it's a small subset of ImageNet, and the training classes and test classes look fairly similar. Okay, so we have things like dogs and mushrooms in the training classes, and at test time, we're learning about new classes that include things like vases and crabs. Okay, and all tasks have the same number of classes, right? So we have like 3 classes in each of these evaluation tasks, and the same number of shots, so 1 each. And the tasks are class balanced. Okay, so that means we have the same number of examples for each class. So just to give you an idea of methods that are used here, one of them is prototypical networks. So this is a kind of metric learning, which has the underlying idea of metric learning is that images from the same class should be closer to each other in the representation space than images of different classes. The notion here is that we're going to take an image and map it through a deep neural network to a representation space that's being shown here on the right. And so each of these dots on the right, colored dots, represent examples from classes. So over here in the green, we have 5 examples from one class, orange at the top of examples from a second class, and down below 5 examples of a third class. And this is in this representation space. It will be a high dimensional representation space here, just shown as 2-dimensional for visualization purposes. Then the idea in prototypical networks is that points that belong to a single class will cluster around a single prototype representation. So here we see the prototypes shown in black for C1. That's the prototype for the first class. Up here we have the prototype for the orange or the second class. And down below we have C3, the prototype for the third class. And that's just the average of the representations in this space. Then we can classify new points like the X being shown here. It gets mapped to the same representation space. This white little circle then is the new point in the representation space, and it is just classified based on its distance to the prototypes using this softmax function. Okay, so that's prototypical networks. Just give you an idea. And the idea is that these are all new classes. We haven't seen these classes. We just get 5 examples in this case, so it's 5 shot of the 3 classes, and we're able to classify very well examples. There's 2 equivalent interpretations of this. When we use the distance between the prototype and the new example, this phi of x is the new example, and this is the prototype. We can interpret this in a probabilistic framework, thinking of it as a mixture density. So it's like we have a Gaussian class conditional distribution for each of the classes, and the posterior distribution over the classes is given by this mixture model. We also have a linear model interpretation that we can not think about it so much in probabilistic terms, but think of it as weights and biases in a neural network where the weights and biases are determined by the prototypes. And so it's a simple mapping of from the representation layer to the output layer. In terms of results, so this is as of a few years ago when prototypical networks was defined. They're on 2 standard benchmarks, one called Omniglot, which is handwritten characters, and the other one is the mini-ImageNet that I mentioned before. And it got state-of-the-art results on accuracy, both for 5-shot and 1-shot examples. So we were very happy to find out when we worked on this that this didn't just apply to images, it also worked well for speaker recognition. And speaker recognition few-shot is very important there too. So we may have new users to a system. So every new user is a new kind of class in a way. And what we want to be able to do is decide who is speaking in each time. So speaker verification, right? We want to say, is this the right person, for some automated speech task? And we don't have many examples, so we're registering new speakers. There's also, speaker identification is another one. Can we classify amongst K different speakers, like in dialogue transcription, who's speaking when? Okay, so those are good examples of few shot recognition. And just to give you an idea, is that this is a paper from ICASP a couple years ago, and in this case, Protonetworks also did very well on some of the standard benchmark data sets in speaker identification. Okay, so this is just a bit of history. So the early benchmarks and approaches have become very popular. So these are a few of the original papers in this few shot classification world: matching networks, our prototypical networks, and then MAML, or model agnostic meta learning. They've all gotten a lot of citations. Ours is a little bit less, not really sure why. But so they've become very popular, these early benchmarks. But now we want to take a step back and say, okay, where are we? And what's happened in the time since then is, like prototypical networks, MAML, they're very simple approaches, and people in the intervening years have developed much more complicated models and elaborate models that actually improve the benchmark performance, right? But at the same time, others have shown that these benchmarks can be solved, so-called, that is, get really good results without using the support set labels at all. Okay, so this is some work that showed that, just with kind of unsupervised approaches, you could do very well. The second thing is that the success of MAML, so MAML is a kind of approach where you have a representation like I described, mapping the input to a representation space, and then you do a little bit of adaptation in that space. That's the meta learning part of it, to for each new task, each new episode. Right, and people showed that the success of MAML was largely due to that first stage, the feature reuse across all of them, rather than the rapid adaptations. The meta learning actually was not too important. Okay, so that suggests you can solve the test task without doing any kind of tailoring of the feature extractor. So it looks like all you need is like a good deep network, and you've solved your problem. All right. So the questions, though, is that I don't think that that's the final answer in this setting, and because really what we want to do is extend to less constrained and more realistic environments. And the question is, what kind of new ideas and approaches will facilitate generalizing this few shot setting? So I'm going to tell you about a few results in this area that we've been working on in the last couple of years in terms of generalizing the setting. Okay. And the first one is considering the question about uncertainty in few shot learning. So uncertainty is really important in few shot learning because, as we've said, you only have a few examples of these new classes you're trying to learn about. So it's very important for the system to be able to know what it knows and knows what it doesn't know. All right, so you don't want to get overconfident classification in this difficult few shot scenario. On the other hand, there's been some work showing that neural networks typically aren't very well calibrated. All right, so the calibration here means knowing what it knows. So we want the system to be confident when it's correct and have a lack of confidence when it's incorrect. Okay, so the degree of confidence should be in proportion to how the probability that the system is correct. Okay, so that's what well calibrated means. But in scenarios like few shot learning, where we have few labels, the systems tend to make mistakes. Okay, when you have a difficult enough problem, it turns out the system is not going to do that well. So the representation of model uncertainty is a key concern in few shot classification. So I'm going to tell you about some work we've done in this area. So in few shot classification, there's been a number of approaches that are of trying to get principled models of uncertainty. Bayesian approaches are one example in there, where you have a kind of Bayesian approach is that you have a distribution over models that are proportional to the prior probability and likelihood given the data, right? And one kind of Bayesian approach is Gaussian processes. So there, the assumption in Gaussian processes is that we have a Bayesian model where it assumes that the function values are jointly Gaussian. So I've illustrated that here on the right-hand side of the figure, where imagine we have data shown by the points here in the top left, So we have different, each data blue dot here is a different example, right, for different values of X, and then Y is the output that we're trying to estimate. We start with prior distribution. So this would be like a linear regression problem. We have a prior distribution over the function. So over different kind of linear linear estimates for this X to Y mapping. Then given these data points, though, we get a predictive posterior distribution that's shown by making sure that the linear regressor here goes through the data points, right? But so that's the likelihood. It has to fit the data, and it also, is a function of the prior. So we end up with a posterior distribution. It's a predictive posterior for each point. We get this posterior distribution F over here. Okay, so this is assuming that what we get is that for every value of X, we have a Gaussian distribution over what Y is. Okay, so that's why it's a jointly Gaussian. One unfortunate thing about Gaussian processes are really elegant. One problem is that they scale cubically with the number of data points, so they're computationally demanding. But the nice thing is that that's not a real problem in few-shot classification because we only have a few labeled points, right? So therefore, it's a very nice setting for Gaussian processes. However, Gaussian processes are typically applied to regression problems and not classification problems, whereas what we're dealing with in few-shot classification is we want to decide which of the few new classes of the 3 or 5 or however many classes we want to discriminate between, what's the probability over those. So that's the softmax likelihood. And inference in Gaussian processes is intractable for this softmax likelihood. So we've done some work recently with my student Jake Snell, presented at ICLR this year, showing how we can combine augmentation and a new kind of pairwise likelihood to get a approach of Gaussian processes for few-shot. So here's just one example of the results. I'll skip the details of the method. But as I mentioned, calibration is a goal. So calibration is shown here in the top row. So calibration on the x-axis, you have the model's probability. All right, and that is the model's probability that the particular class. So this is, take the example of you have a softmax likelihood, and you're looking at the probability associated with the class that is the most likely class. Okay, so that's the highest probability of all the classes for that particular example. And what you'd like to do is have calibration so that the accuracy, so when the model is very confident that the system is very accurate. So that's, whereas when the model is not very confident, so the highest probability class is low in this on the x-axis, that the accuracy is also low. So you'd like the accuracy to match the probability. So that's this diagonal line here. And what you see is that standard methods like baseline plus is a method that doesn't have any kind of uncertainty notion. In fact, just trains some offline classifier. The aforementioned prototypical networks, other kinds of Gaussian process approaches aren't. These prototypical networks, turns out, is pretty well calibrated. These others too aren't. And then what you can see is that Bayesian mammal is pretty well calibrated, and other versions of a Gaussian process, in this case, another version isn't well calibrated, whereas ours is. We've also examined things like robustness to input noise. So it's another thing of uncertainty quantification. How much can we kind of perturb the inputs and have the system be robust to that? And so we've done some investigations of this on different data sets and shown that our method does quite well, competitively with the others in terms of robustness, as well as on another question, which is out of episode detection. So when we have examples now in an episode where some of the examples belong to the classes, the novel classes that are being learned in that new episode or that new task, and some of the examples may not belong to those at all. And so now it's a much harder task. You have to say, which of the classes does this example belong to, or does it belong to none of them? Okay, so that's out of episode detection. It's another important aspect of uncertainty quantification. Okay, so that's one set of work, is like trying to build much more robust models in terms of uncertainty. Now we want to look at diversifying the tasks. So Omniglot and mini-ImageNet has been good in the sense of drawing a lot of people in to work on few-shot learning, and there's new techniques for solving it, but they don't really capture the ability to learn diverse classes and classes that aren't immediately related to the training classes. So we want to start addressing this further as well to move the needle in this agile machine learning goal. So to do this, there's a very interesting data set that's been proposed that now is, you think of it as a meta-dataset, because before we talked about working on like mini-ImageNet or Omniglot, these first two shown here. You can also do it separately on aircraft or birds, right? Images from different data sets. Now, meta-dataset, the idea is you want to be able to do well across all data sets. Okay, so it's really a much more difficult task. And then we can even test it on training on these first 8 data sets and testing on these last 2, holding out those for evaluation. That's now we're testing on data sets that are very different than what is trained on. So this is, again, a real test for how well we can generalize to new classes. That is, on building more agile models. So within the metadata set, there's kind of 2 types of test tasks. One of them is what we call weak generalization. So that's when we're sampling held out classes of one of the 8 training classes there, training data sets there, okay? So we can train up on birds or on Omniglot, and then the evaluation task will be other unseen classes, but from the same data sets that were used during training. Stronger form of generalization is we want to sample from a held out data set. So now it's like I was showing you before, we're going to train up on, let's say, 8 data sets, and now we're going to have test classes that are drawn from a brand new data set. Okay, that's so-called strong generalization. And that's very challenging. So how are we going to tackle strong generalization? So when there's a large gap between the test tasks and the training data, and just using the same feature extractor isn't going to work very well. So we don't, and we can show you, we have results that show that. So what we need is a mechanism that's going to adapt the feature extractor for different test tasks, okay? So it's a more flexible version of this. So towards this aim, we developed what's called a universal template. So here the notion is that you have a model that's the same model that's going to be used in a way, and that's with this universal template layer. But in between, we have some flexibility, some way of inserting things that are dependent on the particular data set. So we might have a specialist layer that's dependent on ImageNet, okay? And then a second one that would be dependent on the flowers, another data set in metadata set. So here the notion is that we're mixing together things that are universal with something that's specific to some of the data sets. We call this FLUTE, for few shot learning with a universal template. And that's a recent paper that just got accepted to ICML. And why is this a good way of learning diverse classes? Well, one thing is that we're able to reuse the template's building blocks. So we, in a sense, we have the same kind of feature extractor, but we're adapting it and kind of modulating it to, for each data set. Another approach would be to train a whole new feature extractor from scratch for each one of those, but that's very inefficient and wasteful because there are going to be shared characteristics we're assuming between some of the data sets, right? So we want to have some combination of sharing with some specialization. And we also, rather than just having something at the top of a feature extractor that modulates it, we found it much more effective to have several levels of representation that are going to be adapted, rather than just fine-tuning the topmost layer. And again, we have a whole set of results. I'm going to focus on one, which is looking at the strong generalization question. So now we can say, okay, what happens if we train on 8 data sets and test on classes drawn from novel 2 data sets? Turns out that so this is a comparison of FLUTE to 2 state-of-the-art methods that do more of what I was talking about before, that train either separately on each of the data sets or do some other kinds of mixing across the data sets. So these SUR and URT are these other baselines that are state-of-the-art for metadata set. And FLUTE, it turns out, does significantly better than them on the strong generalization, the most challenging setting. They both get around 68%, whereas FLUTE is getting an average of 73% on these challenging settings, 73% correct. It also does, so in general, its accuracy on metadata set on the average makes it the kind of state-of-the-art approach on this challenging setting. Okay, so I want to tell you about a third way we can make systems more agile, and that's to look at more natural learning paradigms. So one thing that's unnatural about few-shot is that this idea of having this training phase and then test phase, right? And we test separately on each set of new classes. In more natural learning, we're learning all the time online, and we're kind of training and testing all the time. And it's more incremental. That is, we're going to see some examples of new classes, like as we see in few-shot, and we're going to also see examples of old classes. That is done in standard kind of, machine learning, standard kind of classification. So incremental means we're going to be incrementally considering new classes as well as old classes. Also, we want to build something this is the few-shot idea, where we're going to have just a few examples of these new classes, right? We want to have something that doesn't need tons of examples of new classes in order to do pretty well. We also want to be able to cope with unlabeled data, right? So we aren't always having somebody telling us what the right answer is for every class, right? So we want to be able to work in a semi-supervised setting where we're going to get some labeled examples and some unlabeled examples. And finally, it's continual, right? So we're going to be building through continual experience through the world. So let me tell you about a recent paper that we just presented at iClear on this idea. So imagine we have, somebody, the setting is, somebody's coming into a house they haven't seen before. They're walking through the house and they're learning about the objects in the house. Okay, so let's say the agent or the person starts in the kitchen, right? So it's wandering around the kitchen and it's seeing things. So I'm going to tell you about this paradigm as we've set it up to learn about objects in the kitchen to start with, right? So the agent or person encounters a cup, right? So it sees an image of a cup and it has to recognize it and say that's a cup. It's never seen any, in this case, it's starting fresh, right? Tabula rasa, it hasn't seen any kind of classes before. So this is the continual idea. So it has to say, this is a new class it's never seen before, right? And we're going to call that class 1, first class it's learned about. Now it's going to encounter a plate. It sees a plate, that's a new class. It's going to say that's class 2. Now it sees another cup and the agent should say, oh, that's class 1, okay? But the agent makes a mistake and says, oh, that's a new class. I've never seen this class before. So now we see this dashed line here, the dashed line instead of the dotted line with the one, instead of the solid line with the 1 inside of it. The dashed line means it might not get a label in this case. Okay, so this is getting at the semi-supervised idea. Then it encounters a plate and it's supposed to say it's class 2. All right, so this is the scenario. It's going to constantly see new objects, say, is it a class that it's seen before? If so, which class is it? Or is it a new class? And the agent is going to get labels for most of the examples, but it's going to have some unlabeled things as well. Okay, so this one will be an unlabeled example. And it keeps going and going. And the evaluation then is we're constantly evaluating it, right? It's not episodic in the sense it's constantly saying, when it said new, was the right answer new? When it said class 1, was the right answer class 1? So as you see, it made a mistake here where it said new instead of class 1. Then, so it's going to see a whole bunch of objects in the kitchen, then it might move to another room. Okay, so it's going to switch to a new context where in the kitchen, the kind of classes that it sees are correlated with each other, right? It sees cups and vases and whatever it sees, sinks and plates in the kitchen, right? It's going to see all kinds of objects there. So the kinds of classes that are related to each other. Then it's going to move into the office, walk around in the office and see a bunch of objects in an office. Then go into a living room. So it's going to see new objects consistently in new environments, right? And then it may come back to the office and come back to the kitchen, in which case when it comes back to those things, it may see classes that it saw before. It could also see new classes. So this is the incremental idea. It's going to see a combination of new and old classes, right? We call this wandering within a world, or online contextualized few-shot learning. So what's a good model for tackling this very difficult scenario? So we developed a model we call the contextual prototypical memory. And at the high level, it has a few components. The first component is the same as what we've talked about before. We're going to use a kind of convolutional neural network, a deep neural network that maps the input, which is the visual input, to some representation, right? And then it's going to, there's also going to be an RNN, a recurrent neural network that it handles a kind of short-term memory. This is good at temporal context, saying that, well, if it's wandering in the kitchen, for example, what it's seeing might be related to what it saw before. So there's some temporal order to this. The examples now aren't being drawn identically and independently distributed. There's some temporal context that's important. Okay, so that's captured by the contextual RNN, as we call it. And then there's a prototypical memory that is a kind of long-term memory or semantic memory that's going to remember about different classes. So here we can see you have class 1 and class 2, class 3. We're going to use, they're represented by prototypes in this representation space. And we're going to take the representation in the RNN, combine it with the CNN, and map it to this prototypical memory and be able to classify by looking at how well this new example that it's seeing now relates to the old examples, much as what I described earlier for prototypical memory. So how do we learn about examples? So how do we store prototypes? So this is where, we take a cup and we map it to that space. We want to say, is this an example of a previous class or is this new? Right. So it's a hard example. Like I said before, it's like the out of episode thing I mentioned earlier. It could be that it's seen cups before, and therefore we want to adapt the prototype for class 1, that's cup, to incorporate this new one. So we want to consolidate the memory. Or it could be that this cup is something new. And so now we want to differentiate it from class 1 and have it be a new prototype in this space. Right. So in this case, it's class 1. It's kind of within the confidence intervals. Think of it as you have confidence intervals around each class and around the prototype for each class in the prototype memory. And if it's inside that confidence interval, we're going to consider it as part of that class and consolidate the representation to incorporate that. Right, so that's an example where we change the prototype to incorporate that new example. Okay, we also can incorporate a forgetting mechanism to say, well, if it hasn't seen these things before, we want to have, because this is continual, we don't necessarily want to remember everything, and there might be some advantages to freeing up space in this prototype memory for new things. So things that are kind of old and stale can be forgotten. A very difficult problem in this space is how do we learn from unlabeled examples? And so this is the unsupervised portion of the things that are semi-supervised, right? Some of the examples are unlabeled. And this is very challenging. Part of it, so you can think of it as a reading and a writing operation. A reading operation is happening when we want to decide if something is new or old, okay? So there we use this idea of the confidence interval. So we have these classes, and beta, you can think of as a parameter that says, well, what is the radius of, or for the confidence interval for class 1? All right. And so when we're reading out from the prototype, if the new example in this space has a location as shown by the star here, is within that confidence interval, then we're going to read out and say that's an example of class 1 with some confidence though, right? So there's, again, this is the uncertainty representation. As we talked about earlier, it's going to have to output an example, but it can also output a confidence associated with that prediction, right? So that's a reading operation. At the same time, we have to write new classes. So it could be that we've seen a class, or that we've decided that something is new, but we don't actually have a label for that class. So that's the writing operation. We want to now define a new prototype, even if we're not sure that it's a new prototype. So that's a very dangerous operation, right? Because we can be inventing new classes when they aren't really new, they're old. So that's a problem both ways. Both it could corrupt, that it's not consolidating the way it should, right? Maybe this example really belonged to class 2, and so class 2 should be adapted to incorporate it. And if we define a new prototype when it shouldn't be a new prototype, then on the flip side, if we define it that way, then now we have this new prototype that is defined. It's that could be a mistake that could corrupt further classifications, right? So it turns out that the writing to prototypes is more conservative. So we're going to only create a new prototype if the based on a radius beta W for writing, it's more conservative, all right? And this is actually, what this means is that we're now going to be more liberal or in terms of creating new prototypes when we're in this unlabeled setting, right? Because the danger of making a new prototype is much less than the danger of incorporating something incorrectly into a class, okay? Because that's kind of corrupting the representation of that class. Whereas if we have multiple prototypes for the same class, that's less dangerous. Okay. We're also going to leverage temporal context. So this is, I think, is another interesting aspect that just emerges out of this. So one thing I didn't mention, but it's true in this case, is that the context is not something that the system is told, but it has to infer. It doesn't, we aren't telling it, now you're in the kitchen, now you're in the office, now you're in the dining room. It has to infer that based on the kinds of images that it's seeing, okay? So in this case, without temporal context, it will see, the representations of the prototypes will be kind of all distributed. So here what we've done is using color to indicate the environment. So red is the office, this blue is a kitchen, and the kind of teal color is the living room. So these are all prototypes that belong in these different contexts. And you can see without any temporal context, these are all mixed up in terms of their locations in the prototype memory. When we have the temporal context, the embeddings turn out to be grouped, or the representations are grouped based on their temporal context. So all the prototypes in the kitchen end up being closer to each other, all the prototypes in the living room closer to each other as well. And that ends up being a big win when we're trying to do discrimination and representation in those things. So this is the idea of leveraging the temporal context, and that emerges from our model, all right? And so the basic idea is now we're going to be, this is to give you in the training, what happens is the model goes through and sees these examples that I showed you before, it predicts these things, and it has to learn how to remember and consolidate these visual concepts. And now it's going to do this through many, many episodes. That's what's being shown here, possibly in, like, this might be in a living room, right? And then, and now at test time, it's going to be in some new context, perhaps, right? It's going to see examples in a whole new context. This could be like a kid's room with toys and cars and shoes, and it's tested on new objects and new environments. All right, so this is a very challenging setting, but one I think that's really important that we want to move towards in our few-shot learning and in general, and kind of building these agile machine learning models. Here's just to give you an idea of what this looks like. We built the environment to do so in a home environment where using a 3D simulator, and these are the images. We call it roaming rooms. So this is a benchmark modeling what I was describing, an agent roaming in different rooms. And you can see that each time there it saw a different box. That was it kind of going to a room and focusing on different objects. So each time it saw that, here, maybe I'll show that again since it went by quickly, right? So now it's each time like if you just look in the middle there, each box is like a new object that it's seeing, right? So it's going to see a couch, then it might see a lamp and a picture, and it has to correctly classify those things. And the red and the white, the red is when it's labeled, and the white was when it was unlabeled. So that was the semi-supervised setting, right? So this is a publicly available data set if you're interested in studying this. And this gives you a visualization of how it's actually doing. It's going to focus on these different objects, and we're also showing now its prediction. And the green means that it's a correct prediction, and so it's predicting it as unknown or new, right? And white is when it's unlabeled, as I said before, and the red is when it's labeled, right? And you get this idea that it's going to see these objects and classify those objects. And one thing to note is that we're going to present the objects, and we also present what's around the objects. So the input to the network is within the bounding box. So we're giving the system the bounding box. We're also giving the outside context separately. So it gets both what's happening directly in that little bounding box, that little region of the image that it has to classify, but it's also seeing what's around it. And that's important for modeling the kind of temporal context. Okay, so you can see that it's mostly getting it correct. That's green, and then sometimes incorrectly shows in magenta. It gets it wrong. Okay. So here's one interesting study of what happens in that model. One issue is memory consolidation. So imagine that what we want to do is say, if we've seen an example and then we see it again right away, right, we imagine the system should do very well. Okay, that is, it's because it's seen it and it hasn't forgotten about it. And it's not that right now we don't really have a forgetting mechanism in here, but the important thing, the reason why it doesn't do well when maybe it's been a long time since it's seen it, is that there's a lot of other things that have been added to the memory. Okay, a lot of new objects and consolidating of the old ones. And so the memory has gotten, in a sense, more crowded. classification task has gotten more difficult. So we have to now classify amongst a whole bunch of different classes. So this is what we're showing here, is that we present a new concept for n times. Let's say n is 1, so we only see it once. Then we present something else for t steps. So t is what's shown on the x-axis here. T is the time since that same object class was last seen. And then when we see it again, how well do we do? So the accuracy is what's shown on the y-axis here. So if we present the object for the first time, and then we test it again, two instances later, you can see that the accuracy with no temporal context is about 88%. When we have the temporal context, that recurrent neural network, the full model, it has up to 96%. So that's the one-shot example. So it's only seeing it once, and then it sees it again after 2. Here's an example where it sees it once. Now there's 50 intervening other things that it sees, and then it sees it again. You can see that the accuracy drops in this case to like 84% for the model without any temporal context, and the accuracy is still around 90% or 88% when it's with the full model, right? So that's the consolidation. Now what happens with 3-shot? What happens if we've seen the example 3 times rather than 1? Then there's these intervening steps, and then we see the example again after those steps. Okay, so you can see there is that the system's performance is much better, right? So that, having seen it 3 times, the memories are consolidated, the representation in the memory is much better, and so it holds on to that memory in a more efficient way. Okay, so the last thing I want to tell you about is on this idea of building more agile models is learning richer representations. So one thing is that we want to have a system that learns about visual inputs, not just based on semantic class discrimination like we're talking about. So always here, we're talking about learning about dogs or cats or plates or hippos, whatever it might be. But there's other situations where we want to learn about more flexible semantic structure. So we have a paper that I'm not going to tell you about that we call Flexible Few-Shot Learning of Contextual Similarity. You can look that one up if you're interested. Instead, I want to take it in a little bit of a different direction of how to learn richer representations by incorporating other available information, such as the sketch of an image, right? So sketches are very interesting. A sketch, so here's an image of a dollar bill, and a sketch, it turns out, captures some visual abstraction. Like, what are the essential features, the kind of salient features? So here's a sketch, right? That doesn't have all the details, but it captures some of the essential features of that dollar bill image. So what we wanted to do was say, the hypothesis that we had was that if we learn to imitate sketching from an image, that'll develop a representation that is a very rich representation, okay? So here's an example of our model. We have a pixel image that's input. We go through a mapping of a neural network, and to a representation Z here. Then we have a recurrent network that's going to actually sketch what was seen in the image, okay? So you can see here it produces one stroke and then sequentially produces the set of strokes until eventually it produces an image that's a sketch that matches the original pixel image. And this can work both for images like that are sketches themselves, but also for natural images. So there's this other data set where we have images like this and we have associated sketches with that image. So again, this is like the dollar bill. Somebody has taken the image and found the essential bits of it, that the squirrel in this case, or the elephant here, and define what constitutes the elephant. So it doesn't have all the details of the original image, but it captures the important visual aspects of it, right? So our hypothesis is that if we can have a representation of this image that is capable of then generating the associated sketch, a reasonable associated sketch of that image, that'll be a very rich representation that will be useful, right? And we found that is, in fact, it's not only useful, it actually is capable of classifying wholly novel concepts. So what we do is we take images like this. These are these Omniglot characters, in fact, that has never been seen before. So this system was trained by looking at, in this case, sketches of different kinds of classes. And now we're going to test it on seeing how well can it do on the Omniglot dataset, which are these hand-drawn characters. So it's never seen any characters before. And we're going to take these representations of this that formed by this network, throw away the RNNs. We aren't actually going to try to sketch these things. Instead, we just want to be able to classify. So we want to do our few-shot classification of these images, of these different characters, based on using these representations that were learned in the sketching model. And it turns out that we do really, really well. And we can consider this a kind of unsupervised learning, right? Because the system has never seen during training, it's like a real generalization to a new domain along the lines of the Meta-Dataset. It's trained on one data set, now it's testing on another data set. So it's a really strong form of generalization we're trying to get at here. And it turns out that, so this is results on the Omniglot dataset, the kind of benchmark for few-shot learning. And this is our sketching model. And what you can see is that we do better on either 20-way one-shot or 20-way five-shot, really challenging Omniglot tasks. Our accuracy beats all of the other unsupervised methods, okay, that are trained in an unsupervised way, not using labeled data set from the same domain. And does almost as well, in some cases, actually beats MAML and Protonet, beats MAML and does almost as well as Protonet, a supervised approach. Okay, and we're using some additional information. So we could say, well, it's not just the original image. We're using the sketch, and so we're saying that this additional information is really important. And the way we're doing it by mapping the image to this representation and then generating the sketch turns out to beat other methods that also use stroke information. Okay, so my last bit here, I think I have like 5 more minutes. I wanted to tell you about what I was saying is the surprising thing. So this kind of domain generalization, where we want to train our model on one domain, one kind of set of classes, and test it on something new. So I talked about that with Meta-Dataset. I just talked about that with the sketches. So this is something where this is a challenging thing that's become a really popular problem in machine learning these days. I want to show you how that relates to the notions about algorithmic fairness. So in domain generalization, we have training data that comes from different domains. Like this is, like I mentioned, a Meta-Dataset. This is another example. We have domains like MNIST or colored MNIST. We have, things like we actually have line drawings. We have office home environments. So different environments or domains. Each has its own distribution. And then we want to generalize well to sparsely sampled or unseen test domains. Okay, so that's the domain generalization problem. Algorithmic fairness is an area where, it's a really important area these days, and because our algorithms have become so widely used in high stakes and high impact settings, we need much more than just accuracy from our algorithms. There's been a lot of research in algorithmic fairness over the last few years. And the general setup is fair classification. So we have X as some data, Y is a label we want to predict, and Y hat is the model prediction. And A, this is what's novel, is that we have some sensitive attribute. Could be race or gender, age, socioeconomic status. And we now want to learn a classifier that's accurate. So the predictions of Y hat match the true labels on some held out test set, but it's also fair with respect to A. There's been a lot of work trying to define what fairness means. I'm not going to get into that. But what I want to talk about is how this relates to the notion of domain generalization. And so there's some surprising synergies between these two areas. So invariant learning is a form of domain generalization where you generalize from training from the test environments or distributions by learning or predicting invariant features across the training environments. And the notion is that if these invariant features are invariant across the different training environments, then they're also going to be useful in the test environment. So that's the hypothesis underlying invariant learning. And one popular method for achieving this is called invariant risk minimization. So you can formulate that as saying if you have some inputs and labels X and Y, where the superscript E says what environment those come from, we want to now learn a transformation of the input space. That's like some deep neural network will say, such that the probability of Y given phi of X is the same across all environments, right? So the representation phi of X for the inputs drawn from one environment, the mapping from that to Y is the same for all the environments E. So the link between invariant learning and fairness comes from taking this environment indicator E and thinking about that instead as the sensitive attribute that I mentioned before, like race or gender, right? And it turns out that many of the definition and algorithms that have been developed to minimize violations of fairness or unfairness have direct counterparts in the domain generalization approaches. So just one example of this is group sufficiency. So this was something that was proposed in fairness a few years ago. We want to match the expected value of y given S of x, some representation of x, and E, or in this case, the E is the sensitive attribute. And we want to do this in a way that, it's the same expected value of y across all environments. That's actually the same definition of what IRM is trying to achieve, okay? Then there's other kinds of links. We have a whole paper on this that you could look up called synergies between invariant learning and domain generalization. So one last thing I wanted to mention is that on the frontiers of fairness research is that what happens if we don't actually get to know what the environment indicator is or what the sensitive attribute is? So that's very relevant in fairness because we have, for example, this is some recent interesting work talking about fairness for unobserved characteristics. So that could be things like, sexual orientation. And that's an unobserved characteristic. So we don't get to see what A is. We don't have access to that identity. So it could be like this, where it's something that's unobserved. It could be unavailable because of privacy reasons. So in the fairness community, there've been a number of approaches that address this. So one example is multi-calibration, where you're trying to achieve fairness to all these groups without having demographic labels. And the way to do that that's been proposed is to have invariance with respect to the worst case group. So the sensitive variable, and so it's more interesting than just, so the worst case group, it's not necessarily that we even know what those groups are, right? So it's not that they're not given, we may not even know what the relevant groups are. And so invariant learning has, so I want to now show you how some of the methods for invariant learning apply to this, or could be extended to this. The one thing is this colored MNIST is a data set that's been developed in the invariant learning literature. We have colors associated with the different digits, two classes of digits, the low digits 0 to 4 and the high digits 5 to 9. And in general, the 5 to 9s are going to be colored green and the 0 to 4s are going to be colored red. But sometimes it's going to be misleading. You're going to flip this, and sometimes the low ones will be colored green and the high ones are red. And so different environments might have different degrees of how misleading they are, of how correlated the color is with the shape. All right, so it turns out that during training, if we train it up on two environments where the correlation between the color and the shape is 0.8 in one environment and 0.9 in the other, and now we test it on an environment where the correlation is 0.1, right? That's going to be a real challenge for a typical classifier, because the typical classifier is going to look at color and say, hey, color is a good indicator. I don't have to try to learn about shape. It's just going to classify based on color, right? But having them, the fact that we have these different environments where that correlation varies is going to be a cue that allows things like IRM to do very well. Okay, so it's going to discover features that reliably predict the class regardless of the domain. So we want to do the same type of thing here where the environment labels aren't known. So that's the analogy we're drawing from the fairness literature, where like sexual orientation isn't known. What happens if we want to do invariant learning when the environment labels aren't known? How can we identify domains that will define domains that will help identify these features? So I think because I'm running out of time, I'll just mention this. It's we have a paper that just got accepted to ICML this year called Environment Inference for Invariant Learning that has a way of doing that finds the worst case environments. And this is analogous to the work that was being done in fairness on finding the worst case subgroups. And it turns out that this model is quite a simple model, and it works quite well. In fact, it outperforms IRM in some cases where the IRM actually knows about the handcrafted environment, knows about the environments, and our method yield doesn't, but our method does better on test for color MNIST, and also on another data set from this domain generalization setting called water birds, where you have birds superimposed on backgrounds, and you have to classify whether the bird is a bird typically found on water or a bird typically found on land. And our system does very well on that as well. And finally, we're also doing some work on invariant learning and fair toxicity classification. So the question here is, can invariant learning methods go the other direction? So before we showed how fairness ideas are useful for invariant learning. So that's one form of the synergy. The other form is, can invariant learning methods actually improve fairness? So we've done this by looking at toxic and non-toxic comments on internet news articles. And here the idea is that comments about sensitive identities are often wrongly labeled as toxic, right? So that's the fairness problem. And we've studied and shown to what extent invariant learning methods can help, right? So things like I am a gay man is labeled as toxic by a lot of these automated moderation systems, whereas if you just say I am a man, it's not labeled as toxic. So that has obvious implications of unfairness to groups. Okay, so to wrap up, most of what I focused on are these points. One is that we want to improve strong generalization. So it turns out that your standard learning approach, expected risk minimization, is currently the king of domain generalization. So there's been these data sets that have been defined and interesting problems in domain generalization. And it turns out that in a lot of those settings, so now we're out of the few shot setting, right? We're in a regular setting where you have domain generalization. It turns out that the standard approach is still the king. So that's a real challenge, I think, for the field, is despite all these efforts to develop things like invariant learning methods, they still haven't shown a real win on domain generalization. And then we want to also push forward on what's the analysis of when something can generalize. We don't really expect arbitrary generalization to new domains, okay? So the question is, under what conditions will something generalize it? And can we develop some theory on this? So we have a paper in that just got accepted to ICML this year, where we look at upper and lower bounds on this kind of when things can generalize. Right? There's some progress on this, but there's this real thorny issue of when are tasks related, right? So that's what's really essential, is that turns out you can generalize quite well when the tasks seem like they have some similar characteristics, and not when they don't, right? You can't expect arbitrary generalization. How do you quantify and try to formalize this notion of task relatedness? I've also talked to you about developing richer representations, like incorporating ideas about sketches. And we'd like to move in the direction of trying to have some hierarchical rich representations. That's something that we're working on currently. And in fairness, kind of an open issue is how can we learn fair algorithms in more dynamic environments? So the standard approach is kind of static classifiers and just coming up with a fair classifier. But the more interesting problems is that we have a dynamic environment. Just like I talked about continual learning and the wandering within a world, we want to also have continual notions of fairness. Okay, that's it. Thanks very much.
Well, thank you very much, Richard. An amazing talk. So please, any questions on the chats, and they will also come up on the Zoom chats, and I will read them out. I have a ton of questions, Richard, but I don't want to hog. But given that no questions there for the moment, let me start. I mean, I like this a lot. What I think you mentioned it, but what do you think would give the biggest boost to few-shot learning? Do you think it's better, maybe massive data pre-trained and unsupervised pre-trained feature extractors, like we're now seeing emerging in lots of areas with contrastive losses, which are doing well in other bits? Or do you think it's kind of being clever about how to use the features in when you get that out and try to identify task-specific kind of
right. So that's a good question. So I think that I certainly think that the use of, as you mentioned, kind of contrastive approaches or kind of unsupervised approaches is very important and interesting. And in fact, that's one of the things that we're studying a lot now, which is to say, so one thing I didn't mention was this paper on the flexible few-shot learning, contextual similarity. The idea there is that, and it relates to the notion of task relatedness, right? So if what you trained on in your big training, kind of offline training set, if you train on ImageNet and you're testing on a new set of classes that are actually related to ImageNet, they're new classes, they aren't the same one, but they're in the same kind of domain. Then it turns out that it transfers very well. So that's this notion of task relatedness, right? So you're trained on related things. And so therefore, you can train up in the offline training that you do, with the developments in self-supervised learning, that can be self-supervised and do almost as well or just as well, okay? But when it's unrelated, it's not clear that that's going to work very well, okay? So the self-supervised learning doesn't work well, so we need to have some other ideas in that space. The flexible few-shot one, what we showed was that even when it's related, okay, that the new stuff is related to the old one. If it's related, but it's not class-based, so the classes are, or not, it's the classes are using new sets of features that weren't features that were relevant in training, okay, in the training classes, then the standard kind of offline supervised approaches don't work that well, but the contrastive kind of unsupervised methods do well. And that's, as you might expect, right? It's kind of saying that if you train a system and it learns to discriminate based on particular features, and those features turn out to be not useful at test time, then the system's not going to generalize well. And so this is a real place where unsupervised learning has a role to play.
I agree. I guess it also makes it very difficult to compare actually techniques once you have a very powerful feature extractor, because the question then becomes, is it the more expressive features that are kind of doing the work, or is it the thing you're doing with it, the smarts that goes maybe in the processing of that?
Right. But even on something like Meta-Dataset, you get some wins by, like, if you imagine you want to look at the strong generalization setting, right? So you want to now train up on 8 data sets and test on new classes from the other 2. It turns out that if you just do the training on mini-ImageNet and try to transfer that, that doesn't do as well as training on all 8 data sets and transferring. But even that doesn't do as well as like what we described here, the FLUTE, which is taking into account. So it's not just training up a good feature extractor, doing something where you want to adapt and take into account information about what data set you're in or what environment you're in and condition based on that. And so treating the kind of environment as something separate to estimate turns out it is important.
Very, very good argument. Thank you. I have a question from Mario Kren. He says, I find the concept learning by imitating for drawings really interesting. I just went through the paper a bit. Could you please go a bit into detail there? What do you even consider a concept? Also, how do you know a concept is new? Thanks.
Right. So yeah, so the idea of a concept is somewhat, not that well defined, I would agree. Let's think of a concept in this case as, where there are some sort of primitives in drawing. And so an example we show there is that the kind of algebra that's observed in language, right? So people have shown this with language embedding, right? It's, let me remember the exact example, right? It was king, something like man is the king is minus female, and the answer is queen, right? And we've done something similar in the drawing example where we take embeddings of elements and we say it would take a snowman that has 2 circles, right? And then we say we subtract off subtract off the embedding of the circle and add the embedding of a square. And then we end up with a drawing that has 2 squares stacked on top of each other instead of 2 circles. All right. So the concept there is, right, whether you can think of the concept as the concept of a snowman being composed of these elements, circles potentially, or squares, right? And so there the system has learned this kind of representation because it's had several examples composed of things like circles and squares. Right?
Very nice.
So that's I don't know if that answers the question exactly, but it gives you some idea.
Yeah, no, very nice. I get one more questions. What do you think about the vision transformers which approach an image as tokens? That's from Barrio, the question.
Yeah. Yeah, so I think the vision transformers certainly are very interesting and powerful and kind of exploding these days in terms of how relevant they are. And I think it is very interesting. Again, there's some notion there of what I was just talking about has to be important, right? There has to be some representation of what are the tokens, right? So what are the kind of individual elements that are important, right? So just like in language, you can do things about words and you're kind of given those tokens, and in vision, it's not clear that you're given these tokens. So having sketches available gives you some access to that. It's a little bit harder to do that just given images alone. But I think the visual transformers are moving in a step towards that direction. But still the problem of defining what the tokens are hasn't been solved.
No.
Right? And I think of, that's been something that's been around for for a long time, right? So one of the original few-shot classification approaches developed by Brendan Lake and colleagues was this probabilistic programming idea where you have a bunch of strokes and you're going to develop a new character by composing the strokes in particular ways, deciding which strokes are there and how they relate to each other. But that presupposed the availability of a kind of stroke vocabulary, a kind of part vocabulary. And so a lot of what we've done in the years since then, that's been 5-6 years now, we've been working on this, where it's really about, can we at deep neural network kind of infer and learn what are the underlying components, right? And so it's still an ongoing question.
Thanks very much. Good answer. I have a question from David Cryle. You started by mentioning the value of knowing what you don't know, i.e. knowing about the uncertainty of estimates. How would you ideally calibrate that, especially in the challenging context of cross-domain few-shot learning, I think, which you mentioned. Right. If you had to construct a powerful benchmark, how would you go about that?
Yeah. So so the kind of testing uncertainty is always hard, right? Because so I mentioned the one thing about out of episode. So that's one kind of test, which is to say, if the system is, if you present examples that don't belong to any of the classes, right? The system should have maximal unconfidence, right? Lack of maximal uncertainty in that case, right? Because it should be like a none of the above, highly confident and assigning low confidence to all of them, right? So that's one kind of test. I think that's a good test. Like it's kind of like the out of distribution test in some way, but it's more specific. It's the out of episode test in few-shot classification. That's one thing. Another one is, this idea that people have done, but we did too in the few-shot one, where we add noise, right? So the idea is, as you add noise, the assumption is that the degree of noise that you add, you would like to see the system's uncertainty to increase as well, right? So these are kind of benchmarks that have been done in the general, people are interested in uncertainty have done this in the general setting. And so we did that in the few-shot setting, both the adding noise and the out of episode stuff that mirrors the out of distribution and the kind of robustness to noise. But I think there's this, they're not completely satisfying, right? You'd like to also have a benchmark that looks at, and another one is that we can do a composition. You can say you can build objects that are compositions of two classes. And what you'd like to do is have the system be, say, it's half one class and half the other class. So that's a kind of a crude way of trying to get at the idea that you have ambiguity between the classes. It's another possibility.
Nice. I have another question from same person. Are you and you learn a realistic noise distribution empirically or from the data? I guess it's referring to adding noise.
Yeah. So this one, the noise isn't we aren't learning from the noise distribution. We're testing it on the noisy distribution. We're actually learning on the original distribution. Okay, that's what we did in our case. So the Gaussian process test that we did was trained on the original data set, and now it's being tested on noisy examples and seeing how it does in terms of, and so that's the noise is one kind of calibration. The other one is the kind of internal calibration that I showed you, which is in the standard benchmarks where there is no uncertainty, there's no noise, the system should be very confident. Then you just internally test the calibration and say, when the system is making a mistake, is it unconfident? And when it's getting it correct, is it confident, right? So that's what good calibration is. Yeah. So there are ways of testing calibration on standard data sets, where these other things like noise and out of distribution are ways of trying to push beyond that to further probe calibration.
But where do you get the noise from? How is it just you add Gaussian noise per pixel? Or
interpolate
images.
Right.
Or...
So there's different ways of making the system more the input noisy in the crude way. As I mentioned, it's just add Gaussian noise, add different forms of noise. Right. You can add occlusions, right? So block out parts of the images and change to how much is being blocked out, and think of that as a form of noise, like masking. And then the other one is, like I mentioned, about kind of composing, right? Combining different ones. And that's like another kind of noise, because you're now composing images of different classes.
Very nice. So I'm trying not to do any product placement, but we're running a NeurIPS competition. So we designed one which is based on traffic and actually has few-shot learning elements.
Right.
Looks at domain shift. So it's tough. But having gone through that, I'm always wondering, do you think there should be other benchmark data sets that should have different characteristics that would help the community?
Yes, there's no question that realistic benchmarks are always very important, right? So, and push the system forward, right? So that's what I was saying, is that the weakness for some reason, the original work in FuShot, focused on Omniglot and mini-ImageNet, which were fine for original prototyping, but now it's really important because we've shown how those systems can be kind of learned in various ways, right? To really push beyond that, we need better benchmarks. And so I talked about a few we've worked on, but I think, like the wandering within a world, which tries to get at the idea of continual learning. But as you're saying, dealing with real world situations like traffic is, having more data sets for FuShot, and where FuShot's important and where uncertainty is important, right? That would be great. So the question would be, can you have in real settings? So getting back to turning the question I got to you, like, how can we set up benchmarks where there's target amounts of uncertainty, right?
Yeah.
So that's so you want the system, so rather than just labeling to say, this is the example, we want some idea of saying, well, how hard this example is. And so people have used, crowdsourcing to say, well, if the degree to which the labelers agree is one way of estimating, target uncertainty. I don't know how you're in your data set, if you have something like that.
No, I think we just have, again, I hate to advertise, but it's good competition. But so we have basically in the hardest tasks, actually 2 challenges. The hardest one is you see traffic movements or movies, if you like, from cities, and then you get an hour from a city you've not seen on.
I see.
And you have to kind of extrapolate. So really, concepts, if you want to call them, like roads, or how does the dynamic flow through, you're given the road network as well. So this is actually a hard problem. It would be a fantastic one if that could be solved. But I like your point. Quantifying that at the moment seems hard, but I felt that, if we had a data set maybe driven by crowdsourced kind of metrics, if you like, or maybe, I guess, a synthetic data set, which I guess comes close to the question we had earlier, where you add the uncertainty, so you know what the uncertainty is, but how relevant that is then yet another question, right? That could maybe one thing, but I'd love if there was a benchmark. Would love to help.
Okay, that sounds good. Yeah. I just looked at the sketch. The chat says, wondering how benchmarks could work for your learned sketches and drawing concepts. How did you evaluate? So, one thing is you could always evaluate qualitatively, right, and see how the system draws things. I think that wasn't our main thing. We weren't trying to come up with a good drawer, and so the FuShot classification test was our way of evaluating it. We're generally classification, right, which is we take a natural image, like I showed you, let's say, of a squirrel, come up with a representation of the squirrel, where our representation is able to generate a drawing that looks something like a squirrel, okay, that captures the kind of visual abstractions that somebody else might have had they seen the original image, that they would sketch a squirrel in this way. We throw away the sketching part, we take that representation, we think of, well, how good is that representation at doing various things, such as classifying, right? So if we take new images that it hasn't seen before, possibly from new domains it hasn't seen before, right? So we train it up, we now test it on cars, right? Could it do a good job of recognizing cars, right? So it's really a classification benchmark that could be tested either FuShot or multi-shot, right? So that's what we did in terms of evaluating it. And we also did some more of the qualitative evaluations about trying to see, if we take sketches, that we take images as input in particular way, like what's happening in the representation space, right? So is there so this gets at the idea of disentangled representation. So you'd like to be able to represent different aspects like orientation or size or these types of things in the representation space. So we showed as if you do these kinds of manipulations in the input space, that what happens in terms of where the images are mapped to an embedding space are kind of simple manifolds that correspond to the manipulations in the input space. So there's some correspondence in terms of how the representations that we'd like, the kind of dimensions we'd like to extract, are being represented in the embedding space, right? So that's another kind of evaluation of inspecting the embedding space as you do manipulations to the input space.
Very nice, very nice. I think that has exhausted the questions.
Okay.
Thank you very, very much, Richard, for a fantastic talk. It was really great. Thank you everyone for participating, and we'll send out a short survey.
Okay, thanks. I enjoyed it. Thanks very much.
Thank you. You take care. Okay.
Bye-bye.
Bye-bye.